Now coming to the addition reactions. We know that benzene undergoes substitution reactions, right? But under special conditions, that is under high temperature and high pressure conditions, benzene also undergoes addition reactions. Let me write. Benzene undergoes addition reactions under special conditions like high pressure, high temperature. Now, what are the special conditions? I mean, what are the reactions that it undergoes under special conditions? Let's see now. The first one is addition of hydrogen. Okay. So in this case, I can give you these reactions. Benzene with hydrogen in the presence of Adams catalyst. Okay. Say at a low temperature of 25 degrees centigrade and a pressure of 2 to 3 atmospheres. Addition of hydrogen across the multiple bonds gives us cyclohexane, right? Now, this same reaction can be carried out in the presence of nickel catalyst also. But here the temperature needed is 160 to 170 degrees centigrade. And of course, a very high pressure is also needed. Even here also we get cyclohexane. Okay. Next. Now coming to addition of chlorine. Benzene reacts with chlorine in the presence of sunlight. Just as the halogenation thing, what we have seen in alkanes, even here also, in the presence of sunlight, the chlorine atoms get added across the multiple bonds to form you already have hydrogen at every corner of the hexagon. Now a chlorine gets attached. Right? So this is how we get 1, 2, 3, 4, 5, 6. Hexachloro cyclohexane, right? So this is also known as benzene hexachloride. Simply BHC. So it is also given as a 666. You can actually see that it has a 6 carbons, 6 hydrogens, and 6 chlorines, right? Also known as lindane, also known as gamaxine. You must be knowing this very well. Gamaxine. Finally, what I would like to say is it's actually an insecticide. Gamaxine used to kill ants, right? Now, this is the addition of chlorine in the presence of sunlight. Let us go for ozonolysis. See, benzene has actually got 3 pi bonds. So, 3 molecules of ozone add across the 3 pi bonds and form benzene triozonide. Look at this. Adding ozone across the multiple bond, right? Now, this is anyway unstable. So, this is benzene triozonide. Now, this with zinc water. Let me first write that. With zinc water, forms, yes. Not only this, see, immediately bond comes here. Even this also. Okay. See, it's actually a symmetric one, right? Check out what is happening. Now, let me consider this area. Okay. HC, isn't it? This is HC. Even this also is another HC, which has actually got a double bond O, right? Say this HC double bond O, C double bond O, H. Three such molecules. Of course, we have gone for reductive ozonolysis. 3 molecules of, say, this ethane diol. Common name is glyoxal. Even acetylene gives this. You have seen IUPAC and the common name. Okay. This is how benzene on reductive ozonolysis gives glyoxal. Now, let me also take toluene. Okay. See, in case of toluene also, let us cut it this way. Okay. And now check out the products that we get. Only in this area we get a different one. This one and this one. Even this one and this one. Both are same. Now check this out. From this area, we get CH3C double bond O. I'm done right up to this. Now another C double bond O, but here you got a hydrogen. CH3, C double bond O, C double bond O, H. Because here you got a hydrogen, right? Now, this is called methyl glyoxal. Okay. Methyl derivative of glyoxal. Now, how about the remaining? They give us the simple glyoxal. Right? That's it. Now, this is the ozonolysis of toluene. Next. Let us consider xylene. You know, dimethyl benzene is called xylene. Let us consider ardoxylene. Right? Add ozone, then cut it. So ozone adds on to xylene across the multiple bond. Now look at this. Even here also, say this one and even this one, both are same. In fact, give us methyl glyoxals. This area, of course, gives glyoxal, right? Now, two molecules of methyl glyoxal, just one molecule of glyoxal. right? Now let us consider the other resonance structure of the same orthoxylene. Let's see what we get. Now look at the positioning of pi bonds. Do we get the same products? No. We get different products. 100% different. It's because of the products of ozonolysis. Actually, no. Scientists actually got a doubt on the structure of benzene. Of course, finally concluded that it exists in two different structures. Kekulé gave two resonance structures for benzene. Okay. Of course, even Devar gave three different resonance structures for benzene. But the actual structure of benzene is a resonance hybrid of all these structures. Okay. Now check out this. So this area is going to give us dimethyl glyoxal. And these two areas, we are going to get glyoxal, right? Let's see. Okay. From this area, we get dimethyl glyoxal. Now, from these two, we get the regular one, glyoxal. Okay. Two molecules. Of course, ozone followed by zinc water. Right? Next. Now it's oxidation. See, within oxidation, let us consider complete oxidation, nothing but combustion. So this is benzene. Combustion is burning completely in oxygen, during which we get carbon dioxide and water vapor. Of course, large amount of heat is also released. Now balance this. 6 carbons, you got 6 hydrogens. 6 into 2, 12 plus 3, 15 oxygens. So this can be written as 15 by 2, or else you can multiply the total equation by 2. But generally, when you say heat of combustion, remember you have to consider just one molecule. I mean, 1 mole of substance. Okay. Then we have oxidation with vanadium pentoxide. Now, this is interesting. benzene on oxidation using vanadium pentoxide at 300 degrees centigrade forms phenol. Okay. Now we have just used one oxygen, so let it half mole of oxygen. Anyway, you'll have a hydrogen at every corner of the benzene, right? Now the interesting one is this. Benzene with oxygen. I mean an oxidation using the same vanadium pentoxide at a temperature 500 degrees centigrade gives an interesting compound. Say initially we get maleic acid. You know what maleic acid is? So this is maleic acid, but you know this immediately loses a water molecule to form the final thing, that is maleic anhydride minus water. Without water is anhydride. Okay. So this is maleic anhydride. In fact, this reaction is very interesting, very important. Okay. So this is oxidation with vanadium pentoxide. Then one more interesting thing, that is side chain oxidation. See, side chain oxidation is a very interesting reaction, which is generally carried out using alkaline KMnO4. Consider methyl group. I mean methyl benzene or toluene. See, with alkaline KMnO4, see these benzylic hydrogens are necessary for this reaction to occur. As long as you got benzylic hydrogens, at least one, this reaction occurs. And interestingly, whatever may be the length of the chain, finally we are going to get benzoic acid. Let me give you all those interesting examples. Take this. No, I've taken ethyl benzene. It of course has the benzylic hydrogens, right? Now, when you got benzylic hydrogens, obviously you get the same product. right? Then, so this is where I actually want to repeat the thing that whatever may be the length of the chain, look at the length of the chain. You got ethyl group, but still you finally got benzoic acid. Even this also, right? See, even in isopropyl benzene, this is famously known as cumene. Even this also has got benzylic hydrogen. Of course, one benzylic hydrogen. Even that is enough. We'll get the same product. Benzoic acid or benzene carboxylic acid. Okay. Of course, the remaining things are cut off. And now let me actually take one more here itself. I've taken a tertiary butyl substituent on benzene. Look at this. You got benzylic carbon, but there are no benzylic hydrogens, right? Since there are no benzylic hydrogens, there won't be any reaction. I told you that the presence of benzylic hydrogen, at least one, is necessary. Let me write that. Yes. You need to have at least one hydrogen at benzylic carbon. No, not just this. We can even have alkenyl. Till now we have taken alkyl groups, right? Now this is alkenyl. Even this also. Alkenyl. Alkynyl also. You can even consider this. Even here also. You get benzoic acid. Okay. Now, even when you have this type of a group, don't check for benzylic hydrogens in these cases, like alkynyl and even this case also. So this is alkenyl, this is alkynyl, okay, even carbonyl also. And there is one interesting reaction. See, when you have a different reagent, see, in fact, this is alkyl benzene. But see what has happened with ozone acetic acid followed by the oxidation with hydrogen peroxide. Interesting is the benzene ring gets oxidized. Look at what has happened. Yes, this is how we can give the oxidation reactions of benzene and its derivatives. Okay. Now, these are the miscellaneous reactions.